As you know, BrainMap is co-sponsored by the P41 Center for Mesoscale Mapping, housed here at Martinos. But I will let our own Dr. Susie Huang to introduce our speaker today. So very good to have you all, and thank you so much for being here.
Thanks so much, Abbas, and thank you everyone for joining today in person and online. So it's a real pleasure for me to introduce Dr. Congyu Liao from Stanford. He was a postdoc here actually for a few years before the pandemic. Congyu got his PhD from Zhejiang University in biomedical engineering in 2018, and then joined Cowan Setson Pop and the MR Pigs group as a postdoc here. When Cowan left for Stanford, I think Congyu continued and joined there and became an instructor. His expertise is really focused on MRI data acquisition and image reconstruction, finding novel ways to acquire MRI data that will push the limits of spatial resolution and sensitivity. And he was most recently awarded an R01 grant to do mesoscale quantitative and diffusion imaging in the developing brain. And so he'll be speaking to us about this topic today. So yeah, just want to welcome him and encourage all of you guys to welcome Congyu today as he visits. Thank you.
Thank you for the introduction. I'm honored to have the opportunity to present my research on high-fidelity, high-resolution, quantitative and diffusion MRI today. So before I begin, I would like to provide a brief overview of my professional background. I have been working in MR physics field for 11 years since the start of my PhD program in 2013. Okay. Under the supervision of is that okay? Under the supervision of Dr. Jiehui Zhong and Dr. Cowan Setson Pop, having trained on both Siemens sites, Zhejiang University and MGH, and the GE site, Stanford University, I'm well versed in the technologies of both major MRI vendors. My long-term research goal is to establish a high-quality independent research program on developing quantitative and diffusion MRI techniques. These techniques aim to map out brain microstructures for clinical and neuroscientific application. This goal leverages my expertise on MR hardware engineering, pulse sequence programming, imaging acquisition and reconstruction algorithm, and post-processing analysis. On this front, I have put in significant effort to refine pulse sequence and the reconstruction technique for both Siemens and the GE scanners, including the creation of high-resolution 3D MR fingerprinting package and high-resolution G-slider diffusion MRI packages. These packages are now being distributed over 50 research and clinical sites worldwide. My research has resulted in over 50 journal papers, including 10 as first author, receiving over 1,600 citations over the past 5 years. Recently, I was awarded an R01 grant as a PI to apply our proposed mesoscale quantitative and diffusion MRI techniques for studying infant brain development. So today, my presentation will focus primarily on my two main research fields, quantitative and diffusion MRI. Sorry. Sorry, let's move this. Sorry. Oh, there we go. I apologize. So I just want to. There we go. I'm sorry about that. Oh, okay. Okay. So today, my presentation will focus primarily on my two main research fields, quantitative and diffusion MRI. I will begin by briefly introducing the new techniques I have developed in this field. Following that, I will discuss how this new technology being applied in clinical and neuroscience applications. Finally, I will share some collaborative projects on quantitative and diffusion MRI we are currently engaged in. So first, let's begin with the first section, precision quantitative MRI. So compared to the conventional contrast-weighted images, quantitative MRI could image underlying quantitative tissue parameters. This approach offers more precise and repeatable information for quantitative analysis. Magnetic resonance fingerprinting, or MRF, is a novel quantitative MRI method to obtain multiple tissue parameters simultaneously. MRF utilize randomized flip angle trains and TRs along with incoherent undersampling. By simulating all potential signal evolutions within a fingerprint dictionary, we can match the undersampled data to this dictionary. This process allows us to accurately estimate tissue parameters such as T1 and T2 relaxation time. The MRF technique originally proposed in 2013 began with a 2D spiral acquisition. The initial version still requires about 10 seconds per imaging slice, resulting in about 30 minutes duration for 1 millimeter isotropic resolution whole brain scan. So to enable fast, high resolution MRF scan for whole brain quantitative imaging over the past decade, my colleagues and I propose a series of advancements in imaging acquisition, reconstruction, and the sequence optimization techniques. For example, beyond the conventional 2D spiral MRF acquisition, we propose 3D volumetric encoding trajectories, such as 3D stack of spirals and the 3D spiral projection images. This volumetric encoding trajectory was used for better SNR and the data undersampling across KS, KY, KZ, and the temporal dimensions. On the reconstruction side, we integrated parallel imaging and the subspace low-rank reconstruction into the MRF reconstruction. This integration not only significantly accelerated the image speed, but also improve the overall image quality. To improve the accuracy of parameter estimation, sequence optimization methods such as chromoral bound were proposed to optimize the MRF protocol, such as flip angle trains and the TR trains. This technique significantly improve the image quality, accelerate the image speed, and enhance the image resolution. So with this major advancement, where are we now? We are now capable of acquiring whole brain 1 millimeter isotropic resolution T1 and T2 map in just 1 minute and 55 seconds, and 0.66 millimeter whole brain MRF in just 4 minutes and 19 seconds. If we zoom in one of the axial slices, we can see actually the increased resolution of 0.16 millimeter acquisition could better visualize the subtle brain structures as pointed by yellow arrows. This result demonstrate that actually we have sufficient SNR to acquire such high resolution on clinical 3D scanner with efficient continuous volumetric acquisition and the pooling of data in joint reconstruction. To improve the accessibility of our proposed 3D MRF sequence and the reconstruction techniques, I package the 3D MRF and share them with multiple sites. Currently, our 3D MRF acquisition and the reconstruction package are compatible with Siemens 0.55T, 1.5T, 3T, 7T, as well as GE 3T scanners. Currently, over 50 sites are utilizing our resources. So once we have developed this MR technique, we aim to use this MR technique for clinical and neuroscience applications. The first clinical application we are doing is trying to improve the diagnosis of epilepsy through MRF. Mesotemporal lobe epilepsy, MTLE, is the most common form of focal epilepsy. Hippocampal sclerosis, or HS, the primary cause of MTLE, account for about 40% of adult epilepsy patients. So conventional MR evaluation using T1 and T2 contrast-weighted imaging is a powerful tool for HS diagnosis. However, there are limitations of contrast-weighted images to consider. This contrast-weighted imaging may not sensitive enough to detect subtle lesion changes, and they may potentially miss cases of bilateral MTLE. Quantitative T1 and T2 maps could enhance the diagnostic sensitivity by identifying increases in T1 and T2 values in HS lesions, thereby improving the sensitivities. However, traditional quantitative MRI is encoding intensive. It requires long acquisition time, which is a significant drawback. So in this project, my aim is to improve the diagnosis of HS through MRF. We compare the results of MR fingerprinting with traditional visual assessment of T1 and T2 weighted contrast, T1 and T2 weighted images. Within just the 2.5 minutes MRF acquisition, we can achieve a diagnostic accuracy rate of 96.9% with MRF. This is a substantial improvement over accuracy rate of 69.7% achieved without MRF. As indicated by blue arrows, MRF not only provide improved accuracy rate by clearly highlighting the increases in T1 and T2 maps, but also surpass the traditional T1 and T2 weighted map where changes are less significant. This MR result demonstrates MR's potential in improving accuracy and sensitivity compared to the traditional visual assessment of T1 and T2 weighted MR images. Let's explore this further. First, let's look at the diagnostic pipeline implemented in this study. We scanned 33 MTLE patients and included 30 healthy subjects as a control group in this study. Each participant underwent a 2.5 minutes MRF acquisition, followed by a standard clinical protocol, totaling about 15 minutes per session. Using the MRF data, we apply a tissue fractional segmentation, which automatically highlight the suspicious HS lesions. This data, along with quantitative MRI maps and the clinical contrast-weighted imaging, are then sent to clinicians to further aid in their final diagnostic decisions. Here we present the results, the tissue fraction map and the quantitative T1 and T2 maps from healthy subjects and a patient with unilateral HS. In comparison to the healthy subjects, the HS patients show higher T1 and the T2 values within the HS lesions. Notably, the red arrow point the hippocampus, point the suspicious lesion in hippocampus, which automatically distinguishing the changes. We further analyze voxel by voxel histogram of normal hippocampus, suspicious HS lesions, and contralateral hippocampus of HS patient. Our findings suggest that the control both T1 and the T2 values of contralateral hippocampus align with those observed in normal hippocampus of healthy subjects. In contrast, the suspicious HS lesion shows higher T1 and T2 value, confirming the potential pathological changes. Recently, we further extend our data sets. We are now include 51 MTLE patients and 50 healthy subjects in our study. We then perform volume-based morphometry using our MRF data. After acquiring this MRF data, we can synthesize a T1 weighted MP range using block equation. This synthesized T1 weighted imaging can be then used for substructural segmentation using free surface software. We then analyze the average T1, T2, and the volume proportion of all substructures of brain for all the patients and the healthy subjects. Notably, we found that the HS lesion showed a higher T1 and T2 value and a decreased volume proportion compared to the healthy subject in this study. So in conclusion, in this project, our result showed that MRF could improve the accuracy and the sensitivity compared to the traditional T1 and T2 weighted imaging in epilepsy diagnosis. Next, I will introduce the second project of my quantitative MRI research. I want to explore the potential of integrating a new quantitative map, myelin water fraction, with T1 and T2 mapping using MRF framework. Myelin water fraction is a biomarker to characterize brain's myelination and the demyelination processes. Conventional myelin water imaging utilizes multi-echo spin-echo acquisition and the multi-compartment fitting to extract the short relaxation time of myelin water signals. However, this multi-compartment fitting process is yield conditioned and sensitive to noise, as illustrated here. Additionally, it requires a very long acquisition time to get a clean myelin water fraction mapping. Here is a summary of a relaxometry-based method for myelin water imaging from a review paper. As what we can see, actually, multi-echo spin-echo sequence requires about 12 minutes to acquire just 12 slices to get the myelin water fraction mapping. Therefore, our proposal is to enhance the speed and the SNR of myelin water fraction mapping. Our goal is to achieve rapid, high-resolution, whole-brain quantitative myelin water and relaxation mapping. So the question is, how can we accelerate the acquisition and enhance the SNR efficiency of myelin water fraction mapping? Our strategy is to integrate the VISTA block with MRF acquisition. So VISTA is a specifically configured double inversion recovery sequence. Is designed to suppress the long T1 relaxation time of white matter, gray matter, and the CSF, while preserving signals from short T1 component of myelin water fraction signals. By alternating VISTA and the MRF acquisition, the signal can capture multiple tissue compartments. By using the spatial temporal subspace reconstruction with locally low rank constraint, the whole time series data can be jointly reconstructed to enable the reconstruction of myelin water's images to leverage the encoding and the SNR averaging from all the other time points. Additionally, the whole time series can be used to estimate T1, T2, and proton density map simultaneously. Here is the comparison between standard myelin water fraction map and our proposed VISTA MRI method. As what we can see, the myelin water fraction obtained from our VISTA MRI is consistent with standard myelin water fraction map, but it achieves acquisition time that is 40 times faster, along with higher SNR. In addition to this myelin water fraction map, we can also estimate T1, T2, and proton density map from all the time series. This VISTA MRI allow us to obtain whole brain 220 slices, 1 millimeter isotropic resolution, myelin water fraction, T1, T2, and proton density in just 5 minutes on a clinical 3D scanners. We can even push the resolution further, achieving 0.66 millimeter isotropic resolution. Here is our whole brain 0.66 millimeter ISO T1, T2 proton density and myelin water fraction map in just 15 minutes on a clinical 3D scanner. Compared to the 1 millimeter isotropic resolution, our 0.66 millimeter isotropic resolution could better visualize the subtle brain structures, such as periventricular space as pointed by the red arrows. Once we develop this VISTA MRI technique, we can use this VISTA MRI to study the infant brain development. I'm now collaborating with Dr. Kandanit Grill-Spector from Stanford Psychology Department on this infant brain development project. For optimal SNR, we use our custom-built 32-channel size-adjustable baby coil to acquire the infant data. We then use our 5 minutes, 1 millimeter ISO VISTA MRI protocol to acquire data from a 4-month and a 12-month infant. Compared to the adults' results, both T1 and the T2 decrease, and the myelin water fraction increase during the brain development, indicating the dynamic process during the brain development. Also, in the developing infant brain, rapid T1 and T2 changes present challenges to acquire good multi-contrast weighted images. Using our fast VISTA MRI scan, we can synthesize multiple contrast weighted images such as T1 and PRH, T1 and T2 weighted images, T2 flare, and the double inversion recovery images. Compared to the actual acquired lengthy and PRH acquisition, our synthesized T1 and PRH provide an alternative when the motion artifacts compromise the image quality during the long infant brain scan. Also, we can use our VISTA MRI to study ex vivo brains. This figure shows the 0.5 millimeter T1, T2 myelin water fraction and the proton density map from a 5-month-old postmortem brain. We can see decreased T1, T2, and proton density values and the increased myelin water fraction map in the infant brain cortex, reflecting the strong myelination in the infant brain cortex. We can also target on mature visual cortex, focusing on V1 area. What's particularly interesting is to use our VISTA MRI to observe lines of Janari in this V1 area. That's visible through the decreased T1 value and the increased myelin water fraction value in the myelin water fraction map. This indicates a strong myelination in the lines of Janari in this specific region. Finally, we can use our VISTA MRI to study demyelination in senior individuals. This figure shows the T1, T2, and the myelin water fraction map acquired from a 69 years old postmortem brain. As the red arrow pointed, the dark spots suggest the strong demyelination in this region in the aging brain. So to summarize the first part of my presentation, we discuss how we develop the 3D optimized MRF acquisition and the subspace reconstruction to enable high fidelity, high resolution in vivo quantitative MRI. This enable advancement for clinical and neuroscientific application, including improving the diagnosis of epilepsy and investigating the myelination process in brain development. So in the second part of my presentation, I will focus on precision diffusion MRI. So diffusion MRI is a powerful tool to study large-scale white matter structure and connectivity. But the current 1.2 to 2 millimeter resolution is inadequate for gray matter. Here is the example of high-resolution diffusion MRI. The 60 micron isotropy resolution data could clearly detect the U fibers in the superficial white matter region, while the 2 millimeter resolution DWI cannot detect the U fiber on the same subject. However, diffusion MRI, high-resolution diffusion MRI is very hard to do for a couple of reasons. First, the SNR of high-resolution diffusion MRI is very low. Second, the EPI readout for high-resolution diffusion MRI is very long, which could cause image distortions, T2 star blurring, and long T signal loss. Multi-shot EPI is a promising approach for high-resolution diffusion MRI. However, due to the short-to-short physiological noise, such as respiration, cardiac pulsation, multi-shot EPI continues to be a challenge. So let's look at how we can address these issues. So over the past decade, we have developed advanced acquisition and reconstruction techniques, including G-slider simultaneous multi-slab acquisition and the blip-up and down Buddha multi-shot EPI acquisition with low-rank reconstruction to enhance the SNR and reduce image blurring of diffusion MRI. We also propose to use advanced ACDC shim array hardware to significantly reduce B0 inhomogeneity, and mitigate the eddy currents artifacts. So this technique will push the spatial resolution limit of diffusion MRI and enable mesoscale diffusion MRI, which is important for cortical diffusion studies. So first, I would discuss about the G-slider simultaneous multi-slab EPI. So compared to the simultaneous multi-slice imaging SMS, simultaneous multi-slab could provide better SNR efficiency. G-slider is a simultaneous multi-slab technique with self-navigated alpha encoding. The encoding per slab is performed through sequential alpha encoding and combined using a linear forward-based reconstruction with alpha encoding matrix to create the high resolution slices. The G-slider is designed to provide a high signal in each alpha encoded volume for robust estimation and the removal short-to-short phase corruption without the phase navigator. This G-slider technique is also robust to subject motion. The subject motion can be estimated and corrected every TR of 2 seconds without additional motion navigators. My supervisor, Dr. Colin Sanson-Pop, initially proposed this technique and implement this technique on Siemens Connectum scanner with high gradient, with high performance gradient. To facilitate the broad use of this G-slider technique, I modified the sequence and ported it to both Siemens and GE scanners. Currently, it's compatible for like Siemens 3T and GE 3T clinical scanners. currently over 15 sites are utilizing these G-slider techniques. What you can see, compared to the standard product diffusion EPI sequence, our G-slider EPI could provide a higher SNR at 1 millimeter isotropy resolution with high B values. To further improve the fidelity of the G-slider, I propose two key approaches. Firstly, I significantly improve the SNR and reduce the G-factor noise penalty by using a smooth phase prior in virtual coil grappa reconstruction. Secondly, I increase its robustness to slab boundary artifacts by incorporating B1 plus and T1 correction into the G-slider reconstruction. This figure shows the whole brain 0.86 millimeter isotropy resolution diffusion MRI using our proposed two approaches. This data were acquired on a clinical 3T scanner with 32 channel head coils. This image looks good, but if we zoom in and look into more details, we found that for high resolution diffusion MRI, we still suffer from large image distortion due to the B0 inhomogeneities. So how can we mitigate the B0 inhomogeneities? We propose a slide-by-slide dynamic shimming technique using the AC/DC shim array coils. The AC/DC coil integrates multiple receivers and B0 shim channels, which are driven by rapidly switchable current amplifiers. During the G-slider acquisition, we add two external triggers within each TR to enable the slide-by-slide dynamic shimming using the AC/DC coil. This figure compares the image distortion with and without dynamic shimming. To accentuate the changes in image distortion, the EPI data were acquired using both anterior to posterior APE and posterior to anterior PA phase encoding directions. The green arrows highlight the severe image distortion are much mitigated with a dynamic shimming compared to the standard global second-order shimming. These results are further combined with R4 implant acceleration to achieve a total 10.4-fold distortion reduction, yield the image with outliers closely match that of reference turbo spin echo images. With this slab-by-slab dynamic shimming and parallel image acceleration, we are now able to achieve 1 millimeter whole brain G-slider acquisition with 64 diffusion direction in just 20 minutes on clinical 3T scanners. These high-quality images show minimal geometric distortion in typically problematic temporal lobe, which is beneficial for mapping the connectivity using tractography and mapping the cortical diffusion pattern in these regions. I originally did this with Jason Stockman at MGH on Siemens Skyra and the Prisma scanner. After I moved from MGH to Stanford, Jason helped us to build a new 46-channel AC/DC coil for GE scanner as well, and build the entire shim system at Stanford Center for Neuroimaging. This picture showcases the entire AC/DC shim system at Stanford. So with such advanced hardware, not only can I correct the B0 inhomogeneity induced image distortion, but I also propose to mitigate the eddy currents induced signal dropout in diffusion prepared sequence. Firstly, I introduce a one-time fast spin echo sequence to measure the phase differences between non-diffusion and the diffusion sequence. This scan could provide a fast estimate of eddy current induced phase error. Secondly, Using this phase difference, I put this phase difference into the as an input for shim optimization, creating opposite phase map to compensate the eddy current induced signal dropout in diffusion prepared acquisitions, as indicated by red arrows in this figure. So with such advanced hardware, we successfully correct both B0 inhomogeneity-induced image distortion and eddy current-induced signal dropout in diffusion images prospectively. However, for the side lacking such hardware, the question arises, can we still correct this imperfection using acquisition and the image reconstruction techniques? The answer is yes. We propose blip up and down acquisition Buddha EPI with model-based low-rank reconstruction to enable distortion-free diffusion MRI. In Buddha EPI, 2 EPI shots sample complementary subsets of the K-space, one with positive KY traversal blip up, and the other with negative KY traversal blip down to create the opposing image distortions. Then the B0 and the eddy current information can be extracted using FSL top-up via the acquisition pair. This information can be then incorporated into a joint model-based Buddha reconstruction with structure low rank constraint across 2 EPI shots to generate one distortion-free Buddha images. Compared to the FSL top-up method that estimate the blip up and blip down shots separately, our joint Buddha reconstruction could significantly reduce 20% G factor noise penalty at high accelerations. We then combine this Buddha technique with our G slider technique for high isotropic resolution diffusion were used for a total of 10 EPI shots across blip up and blip down shots per slab. This figure showed the single diffusion direction DWI, colored FA map, and the average DWI at 0.86 millimeter isotropic resolution. Compared to the reference MP range images, our Buddha G slider data retain high geometric fidelity, which is beneficial for accurate core registration of MP range images. So we can further push the Buddha G slider multi-shot EPI to 0.5 millimeter isotropic resolution with higher image gradients. We are now using the G ultra high performance scanner with higher gradient to get a 0.5 millimeter isotropic resolution diffusion MRI. To improve the accuracy of the high resolution diffusion MRI, we are using scope field camera to measure the eddy currents information from diffusion encoding gradients and measure the gradient delays of trajectories and incorporate this information into our model-based reconstruction. Additionally, we propose to use our optimized circular EPI trajectory and advanced structure low-rank reconstruction to further reduce TE and improve SNR. With this major advancement, we are now able to acquire whole brain 0.5 millimeter isotropic resolution diffusion MRI in just 35 seconds per diffusion direction and produce high quality FA map. As shown here. So once we develop this high resolution Buddha G slider technique, we want to use this technique to investigate the microstructure of gray matter. So in the ex vivo study, researchers from Germany use a 10-hour diffusion protocol to scan brain ex vivo brain slab at a 0.25 millimeter isotropic resolution, discovering intracortical fiber running tangentially within cortex. To validate this in vivo, we use our Buddha G-slider multi-shot EPI technique to acquire in vivo whole brain diffusion MRI at 0.76 millimeter isotropic resolution with 2 shells. This zoom-in figure shows the orientation distribution function, ODF, in somatosensory cortex S1 and the primary motor cortex M1 regions. Consistent with ex vivo studies, we found the radial orientation in M1 region and the tangential fiber to local cortical surface orientation in S1 regions. We then project this ODF to multiple ecovolumetric surface and calculate the radiality map at all these surfaces. We found that the radiality is lower in the white-gray boundary, higher in the middle cortical depth, and lower in the pure surface, with lower radiality in S1 region across all surfaces, revealing the tangential fiber in the S1 region. So to summarize the second part of my presentation, we developed the Buddha G-slider EPI acquisition, model-based reconstruction, and used the ACDC hardware to achieve high fidelity, high resolution in vivo diffusion MRI. Using this technique, we can achieve mesoscale diffusion MRI with high fidelity, which is important for cortical diffusion analysis. So in the final part of my presentation, I want to share some collaborative projects on quantitative and diffusion MRI we are currently engaged in. So for the quantitative MRI, the first project is trying to porting our 3D MRI technique to low field 0.55T MRI scanner to improve the accessibility of low field MRI. We redesigned the 3D MRI trajectory with weaker gradient of 0.55T MRI and optimize our trajectory to reduce the concomitant field at the low field strength. With such modification, we are able to get a high quality 1.2 millimeter ISO T1 and T2 and proton density map in just 4.5 minutes at 0.55T. Using these quantitative maps, we can synthesize high-quality multi-contrast weighted images, including MPRH, T1 and T2 weighted images, T2 flare, and double inversion recovery images. I believe this fast quantitative MRI techniques and the image synthesis technique could help improve the accessibility of low-field MRI scanners. Another field we are working on is high-field quantitative MRI. We are now collaborating with Dr. David Feinberg at UC Berkeley on transporting our 3D MRI sequence to the next generation 7T scanners. This impulse scanner equipped with high performance gradient capable of 200 millitesla per meter Gmax and 900 Tesla per meter per second slew rate. It also equipped with high density 96 channel receiver coils. However, implementing 3D MRI acquisition on this impulse 7T scanner is present several challenges. The issue is related to the gradient imperfections, B0 and B1 plus inhomogeneities. So to correct the gradient imperfection, we use a scope field camera to measure the gradient momentum after the spiral readout and also measure the B0 drift caused by the eddy currents. After this measurement, we add a small composition gradient blip at the end of this TR to prospectively correct these gradient imperfections. Also, we did the B0 correction to reduce the image blurring due to the spiral acquisition, and also did the B1 plus in homogeneity correction to significantly reduce the T2 bias in the MRF acquisition. With all this gradient imperfection, B0 and B1 in homogeneity correction, we are able to achieve whole brain 0.56 millimeter isotropic resolution T1 and T2 map in just 4 minutes at this powerful 70 scanners. Here are the results. And using such high resolution, high quality quantitative MRI results, we are able to synthesize MP range that reveals subtle brain.
You can continue, sorry.
Which can reveal subtle brain structures. I don't know.
No, you just go on. I'm sorry about
Okay,
that.
sorry.
Someone's trying to call in, but okay. Let me stop it. Yeah. It's really interesting talk. Sorry, please go on.
Yeah. So this is a very efficient acquisition because we can acquire almost 400 slices across the volume in just 4 minutes. This enables us to achieve rapid and high precision in vivo mesoscale quantitative neuroimaging using our proposed 3D MR techniques. And for the diffusion, high-resolution diffusion MRI, I'm collaborating with researchers from MGH and the University of Toronto. We are using our G-slider sub-millimeter diffusion MRI protocol to detect the silent acute macroinfarct in patients with small vessel disease. As demonstrated in this figure, conventional 2 millimeter ISO diffusion MRI could detect a small acute macroinfarct in the left front white matter. The high-resolution G-slider diffusion MRI could detect the same small acute macroinfarct in the left white matter, but also a smaller acute macroinfarct in the right parietal white matter, which is very helpful using the high-resolution diffusion MRI protocol. And to further improve our high-resolution diffusion MRI, to improve the accessibility of our high-resolution G-slider diffusion MRI, we create a benchmark in vivo diffusion MRI dataset at a 0.76 millimeter isotropic resolution. This data were acquired here using the Connectum scanner equipped with a compact 64-channel head-only coil. The data is acquired using our G-slider sequence with the blip up and the blip down acquisition. And the data acquired like two share with 1260 diffusion direction, enabling the creation of high quality FA map as shown here. Compared to the 1.5 millimeter isotropic resolution, our 0.76 millimeter isotropic resolution G-slider data show much better details of subtle brain structures, such as the white-gray boundary, matter boundary. This data provide a more precise investigation of white-gray boundary and the cortical layer, which is important for cortical diffusion analysis. So to summarize the presentation, I showcase my main contribution on two main MRI research fields, quantitative and diffusion MRI, by synergistically combining advanced acquisition and the reconstruction strategy with newly available hardware instrumentation. We are able to achieve high fidelity in vivo quantitative and diffusion MRI at a mesoscale resolution. This is a powerful tool to improve our understanding of human brain for clinical and neuroscience applications and transfer new insight to public health. So finally, I would like to thank my colleagues and collaborators, and some work are supported by NIH grant. Thank you for your attention.